In an earlier video, we talked about whether or not a bond was polar. And you may recall that a bond is polar if there are two atoms sharing the electrons, two atoms that make up the bond that have different electronegativities, which means one is partial positive and the other is partial negative. The bond is nonpolar if the two atoms sharing the electrons, the two atoms around the bond, have the same electronegativities. If they're identical, then it's a nonpolar bond, and even if they have very, very close electronegativities, sometimes we go ahead and say that's a nonpolar bond as well. Saying whether or not a molecule is polar versus nonpolar is a little bit more complicated of a topic, and it requires some pictures. And let me warn you again, I'm going to draw these pictures, but I encourage you to actually look at models, look at three-dimensional pictures drawn by people who are much better at it than me, or get yourself out your model kit or your marshmallows and toothpicks and hold these in your hand as we go through these examples. For a molecule to be polar, there must be an unequal distribution of the charges, the partial positives and partial negatives. And the best way to explain this is just by jumping in and doing some examples. For example, if I look at the molecule CO2, let me draw the Lewis structure very quickly because I know you're getting good at this. And I end up with two double bonds around the carbon for my CO2 molecule. Two groups is linear. I would describe the electron geometry as linear. Since both groups have atoms attached, I would still describe the molecular geometry as linear. Now, between the carbon and the oxygen is more electronegative. So if I just look at this bond between the carbon and the oxygen, the bond is polar, where the carbon is partial positive and the oxygen is partial negative. This is a polar bond, as we discussed earlier, because the carbon and the oxygen have different electronegativities. But for the molecule, there are two polar bonds, because there's a carbon-oxygen bond this direction as well. And for the carbon-oxygen bond this direction, the carbon is partial positive and the oxygen is partial negative. If I look at this molecule in three-dimensional space, there is a partial negative on the outside positions and a partial positive right at the center. And what happens is these partial negatives on the outside cancel out with the partial positive on the center. There are a couple of different ways of describing this, just depending on what your expertise is. You can think of this as vectors, and the vectors sort of overlap. The partial positive versus partial negative cancel each other out. Or you can think of it in terms of a three-dimensional shape where the center of the partial negatives is exactly the same place as the center of the partial positive. In three dimensions, the partial negatives are centered at the center of the molecule on the carbon, and since the carbon is the only partial positive, that's where it's centered. Or you can think of it as horses. If we have the center of the molecule, where the carbon is, as a stationary spot in space, we can think of the oxygens as little horses pulling away from the carbon. So I have two oxygen horses pulling away from the carbons in exactly a linear fashion, 180 degrees from each other. And if my two horses, my two oxygen horses, are identical, they will pull with equal strength. You can relate this to their electronegativities, which means that the molecule stays stationary. If the molecule does not move, that means it is balanced, that it means it is symmetric, that means it is nonpolar. So CO2 is a nonpolar molecule, even though it has a polar bond, because the polarities of the bonds cancel out. They're centered at the same place, they cancel out, and you can see this analogously by thinking of horses pulling away from the center. On the other hand, I look at an HCN molecule. I did that very quickly because you're getting really good at it. This is also a linear molecule. The central atom is the carbon, and there are two groups, a triple bond and a single bond, and so it is linear 180 degrees. But in this case, the polarity of the two bonds are not identical, and so this is a polar molecule. Another way of thinking of it is that the centers of my plus and minus don't cancel this time because they don't have exactly the same bonds on either side. Or if you want to, think of it as a nitrogen horsey pulling that direction away from the center, a hydrogen horsey pulling that way away from the center, and since the nitrogen and hydrogen are not identical, they are pulling with different strengths. So again, there are a couple of different ways of looking at but this is a polar molecule. Be careful, do not simply memorize linear is nonpolar, because here we see an example of a linear that is nonpolar on the top and a linear that is polar on the bottom. This is really situational. And let me encourage you not just to write a bunch of lines on a piece of paper and look through the lines trying to find out which one yours matches. Look at the molecule. Hold the molecule. Think of it in three-dimensional space to come up with your answer. All right, let's do some more examples. All right, let's look at our trigonal planar arrangement. For example, if I look at the SO3 molecule. Again, I did that really quickly because you're getting good at this, but with SO3, count up my valence electrons, draw my skeleton, count up my valence electrons, put them all around the outside. I run out before I get to sulfur, so I take 2 electrons and move them into the bond. This is the Lewis structure of SO3. There are 3 groups around the sulfur. 3 groups are a trigonal planar. Since all 3 groups have an atom attached, the geometry, the electron geometry, which is trigonal planar because of the 3 groups, is exactly the same as the molecular geometry. It is also trigonal planar. So I'm drawing a representation of the molecular geometry down here with a bond angle of about 120 degrees. Now, the sulfur-oxygen bond is polar, but each of these sulfur-oxygen bonds is polar, and they are each going away from the sulfur in a trigonal planar arrangement around the center, and so this is a perfectly symmetric molecule, which means it is nonpolar. A couple of ways of looking at that. I can think of these polarities as vectors. The oxygen ends up being partial negative, but they're all pulling away with the same polarity. They're horses pulling away from the center with the same strength. The molecule doesn't move, therefore it is a non-polar molecule. The trigonal planar arrangement is perfectly symmetric as long as I have exactly the same groups on the outside. Now, if I were to have a lone pair, and I'm going to stop giving you real examples because you can think of them yourself and you'll come across them in your studies, but let's say I have a trigonal planar electron geometry, but only 2 atoms attached and 1 lone pair, and now I have a bent or angular molecular geometry. Now I have something that is not symmetric, which means it is polar. In this case, I have a geometry that is polar. This is a polar molecule. And so the partial positives and partial negatives don't cancel out. I can think of it as this side down here is going to either be partial positive or partial negative depending on what the atoms are. This position here is going to be the opposite, partial, again, partial negative or partial positive depending on what the atoms are. Or I can think of it if these are 2 horses pulling away from the center, there is nothing pulling away from the top, and so they're going to drag this molecule down. So my horses pulling away from the center are going to drag this molecule down. The molecule will not stay stationary, therefore it is not symmetric, therefore it is a polar molecule. So this is a polar molecule. If I have 3 electron groups, it's a trigonal planar, but if one of the groups is a lone pair, that breaks the symmetry of the molecule and gives me a polar molecule. We can see something similar with 4 groups. If I have 4 groups around the center, that is a tetrahedron electron geometry. And as long as I have exactly the same atom attached in all 4 positions, this is a totally symmetric arrangement and non-polar. But the minute I have a lone pair in any of the positions, if I had a lone pair, that breaks the symmetry, and that gives me a polar molecule. Likewise, if I have, instead of 4 identical atoms around it, if I had an odd atom Now my horse would be pulling with a different strength, which means that this is no longer a symmetric molecule, it's not symmetric, and it's polar. So essentially what you're looking at is you're looking at the geometry and saying, is this molecule symmetric or not symmetric? If the molecule is symmetric, perfectly symmetric in all three dimensions, then it's nonpolar. If the molecule is not symmetric, it is polar. I'm going to let you go ahead and work on the trigonal bipyramid and the octahedral, or we can do some examples in class, but this will get you started with it.